Hello and welcome to this lesson on the foundations of engineering economics. My name is Faiz, and in this lesson we are going to cover these 5 topics. So we will start by learning about simple interest and compound interest. Then we are going to learn about a concept called economic equivalence, which is related to interest. Next, we are going to get ourselves familiarized with the common terms and symbols that are used in engineering economics. And then we are going to learn about cash flow diagrams and how to draw these cash flow diagrams. And finally, we are going to learn about a concept called MARR, which is an acronym for Minimum Attractive Rate of Return. So let's begin. Right, so first of all, we must understand why engineering economics is important to engineers. Now, the simplest definition of engineering economics is it is a collection of techniques that help you compare engineering solutions based on economic basis. So in other words, engineering economics is the application of economic principles that help you to analyze engineering decisions. What's more interesting is that the techniques of engineering economics, the methods that you will learn in this course, can be applied for both personal or professional finances. Now, coming back to the question, why is engineering economics important to engineers? Now, engineers are problem solvers and they solve problems by coming up with solutions, by designing solutions. And these solutions could be in the form of new processes, new methods, new machines, for example. But designing these solutions, coming up with these solutions often involve economic decisions because a certain amount of resources, certain amount of finite resources must be allocated to these solutions. For example, a certain amount of funds or a certain amount of manpower, technical expertise, or a certain amount of time must be allocated to come up with these solutions. So therefore, engineers often come up with multiple alternatives to solve a given problem, and they will then select the best alternative, the most economical alternative to solve that particular problem. So therefore, economic analysis is a fundamental task of engineering. Engineers can no longer be just concerned with the technical merits of their solutions, but they must also be aware of the economic implications of their solutions. So therefore, engineering economics is a foundation for engineers to make good decisions, to make strategic decisions in a competitive business environment. Now let us look at the definition of the common terms that are used in engineering economics. Now the first term is alternative. An alternative is a stand-alone solution for a given problem. So, for example, in a project to generate electricity, the possible alternatives could be a solar farm that generates electricity from the sunlight. Another possible alternative could also be a nuclear power plant that generates electricity from nuclear reactions. Now, both of these solutions, both of these alternatives are stand-alone solutions, which means they can operate independently of each other. Now, the second term is cash flow. So, cash flow means movement of cash, and cash could be moving in, as in cash inflow, or cash also could be moving out, as in cash outflow. Cash flows are associated with the alternative that is being considered. So for example, the cash flows for the nuclear power plant could be the income that the nuclear power plant or the company operating the nuclear power plant receives by selling the electricity that it generates. So that's cash inflow because that's a revenue. And the cash outflow could be the operating expenses, operating costs that are needed to maintain the nuclear power plant. Now let us talk about one of the most important concepts in engineering economics, which is the concept of time value of money, TMV. Now, time value of money says that there is a change in the amount of money over time. So consequently, there is a change in the value of money over time. So money has a time value. For example, the value of 100 ringgit today is not the same as the value of 100 ringgit next year, because the price of things are getting more expensive, and this is due to inflation, and inflation decreases the value of your money over time. Now, the other reason is because when money is invested, those investments are expected to earn a certain amount of returns over time. So for example, if you invest 1,000 ringgit this year, you would be reasonable to expect that your investment would give you a certain amount of return by next year on top of the 1,000 ringgit that you invested. So therefore, time value of money explains the change in the amount of money over time for money that is owed or money that is owned. Now, time value of money is also related to the concept of inflation. This is shown by this picture here, how inflation changed the value of money over time. The price of a cup of coffee in the year 1970 was 25 cents. Just a decade later, in 1980, the price of the same cup of coffee has almost doubled to 45 cents. And by the year 2019, the price of that same amount of coffee, same volume of coffee, and presumably same ingredients that go into the cup of coffee has gone up, has increased to $1.59. This means that over time, you would require more money to purchase, to buy the same quantity, the same amount of product or service. So this shows that the value of money change over time. Now let's talk about interest and interest rate. So interest is the manifestation of time value of money. Interest is the measure of how much the amount of money has changed over time. Interest is the cost of borrowing money, of using someone else's money. So the amount of interest is calculated by the difference between an ending amount that is owed and a beginning amount that is borrowed, which is called the principal. So the formula is given here. Interest, the amount of interest, is equal to the amount of money owed now minus principal amount, and interest rate is the amount of interest as a percentage of the principal. So this is given by the formula here. Now let's look at the different interpretations of interest rate. Now for a borrower, interest is paid. So you have a borrower here, and he borrows money from a bank. He takes up a loan from a bank, and when he repays that loan, he repays it with a certain amount of interest on top of the original amount that is borrowed. Now for an investor, interest is earned. Interest is an income. So for example, when an investor lends his money to a corporation or invests his money in a corporation, he expects to be repaid by a certain amount of interest on top of his original investment. Now let's look at some numbers to clarify these points. So for a borrower, an interest is amount of money that is paid to a lender. So you have a borrower here. He borrows $5,000 for 1 year, and he repays with $5,350. So therefore, the interest amount that is paid is $350, which is the difference between the amount of money that is owed, which is $5,350, minus the principal amount that is borrowed, which is $5,000. So interest rate then is the amount of interest paid, which is $350, as a percentage of the principal amount, which is $5,000, and that gives you an interest rate of 7% per year that is charged on this loan. Now let's look at the example for an investor. So we are using the same example here. For an investor, interest is the money that is earned. You have an investor here. He invests $5,000 for 1 year, and he receives $5,350 for his investment. The interest that is earned by this investor is $350. The rate of return on his investment is also 7% per year, which is the interest that is earned, $350, as a percentage of his principal investment, which is $5,000. Now there are two types of interest. The first type is called the simple interest, and the second type is the compound interest. Now, simple interest is based just on the original amount, which is the principal amount. So interest amount per period is given by the principal amount multiplied by the interest rate. So let's look at a simple example here. You have a $250,000 investment in a 3-year bond at 5% per year simple interest. So interest amount per year in 1 year is given by the principal amount, which is $250,000, multiplied by interest rate per year, which is 5%, and that gives you $12,500 of interest per year. So because our investment is over a 3-year period, so therefore total interest over 3 years is simply given by the interest amount per year multiplied by the total number of periods, which is 3 years. So that gives you a total interest of $37,500 over 3 years. Now let's look at compound interest. What is the difference? So compound interest is based on the principal amount plus all accrued interest, all past interest. So the formula is given here. Compound interest per period is equal to the principal amount plus all accrued interest multiplied by the interest rate. Let's look at the same example here, but this time the interest rate is compounded. So we have a $250,000 investment for 3 years at 5% per year compounded. Okay, so interest in year 1 is equal to $12,500, and this is given by the interest rate of 5% per year multiplied by the principal amount, which is $250,000. But interest in year 2 is slightly increased. As you can see here, interest in year 2 is $13,125. And the reason is because the interest rate 5% per year is now charged on the principal amount of $250,000 plus the interest in year 1, which is $12,500, and that gives you the amount here, which is $262,500. So interest in year 2 then is compounded from year 1 up until year 2, and that gives you this amount here, $13,125. So you do the same calculation for year 3, you will get interest in year 3 is $13,781. And the reason is because, as you can see here, the interest rate of 5% is charged on the principal amount, which is $250,000, plus the interest in year 1, which is $12,500, plus interest in year 2, which is $13,125, and that gives you this figure here, which is $275,625. So that is why the interest in year 3 is increased. So total interest over 3 years then is $39,406. Total due after 3 years is just the total interest over 3 years plus the principal amount, which is $250,000, and that gives you $289,406. So now that you know about interest, let's look at the concept of economic equivalence. Now, economic equivalence says that different sums of money at different times may be equal in economic value. So to demonstrate this point, I have drawn here a timeline over a 3-year period. So you have t equal to 0, which is present time, and t equals to plus 1, which is 1 year in the future, and t equals to minus 1, which is 1 year in the past. So let's say I have $100 now, and the current interest rate is 6% per year. So that means the $100 that I have now will grow into $106 by next year. So if I do the same calculation but reverse in time, 1 year into the past, I would have $94.34 last year. So what this means is that if I had $94.34 last year at 6% per year interest rate, this would have grown into $100 now. So the interpretation is that $94 last year and $100 now and $106 next year are equal in economic value at an interest rate of 6% per year. What this means is that if someone offered you, for example, if someone offered you, you could either have $100 now or $106 next year, it would make no difference which option you choose, because either way you would still end up with $106 next year, provided that the interest rate is fixed at 6% per year. Now let's look at the terminology and symbols that are used in engineering economics. So firstly, we have T, which is the time index that points to a particular year or month or week or day in your timeline. Next, we have P, which stands for the present worth or present value or present sum of money. And then we have F, which is the future worth or future value or future sum of money. The time index for F occurs later than the time index for P in your timeline, because the cash flow for F occurs in the future. It occurs later than the cash flow for P. And then we have A, which is the annual worth, which stands for annual worth. And A is a series of equal and periodic cash flows. So the unit could be dollar per year or dollar per month or dollar per week, which depends on your timeline. And then we have N, which is the total number of periods, which could be years, months, or days, or weeks. And then we have I, which is the compound interest rate, and the unit is percentage per period. Now let's look at this simple example here. Borrow $5,000 today and repay annually for 10 years, starting next year at 5% per year compounded. Let's identify all symbols here. So it should be clear to you that the first symbol here that we have is P, which is $5,000, which is the amount that is borrowed today. Next, we have A, which is the amount of annual repayment that is being repaid for 10 years. So then we have N equal to 10 years. And then we have I, which is the compound interest rate of 5% per year. And then we have T, which is a time index that starts from year 0 to year 1 to year 2 until year 10. And F is not used in this example. Now let's talk about cash flow. Now cash flow is the movement of cash for a particular system or alternative that is being considered. So cash could be moving into the system, or cash could be moving out of the system. Cash inflow is also called the positive cash flow because money is being earned, money goes into the system. So examples of positive cash flows are revenues, dividends, and incomes. So for cash outflow is also known as negative cash flow because money is flowing out of the system. Money is flowing out of the alternative that is being considered. So cash outflow includes expenses, costs, and taxes. So then the net cash flow equals to cash inflow minus cash outflow. So if you have a positive net cash flow, that means you have more cash flowing in rather than flowing out. Your cash inflow is bigger than your cash outflow. And conversely, if you have a negative net cash flow, that means you have a bigger cash outflow rather than cash inflow. So you have more money going out of the system rather than coming into the system. Now let's learn how to draw a cash flow diagram. Now the cash flow diagram is one of the most important tools in engineering economics. A cash flow diagram is the graphical representation of the movement of cash for that particular alternative or system that is being considered. It's very important that the cash flow diagram is drawn correctly. So you start by drawing the time scale that is involved. So for example, I have here a time scale for a 5-year period starting at t equals to 0 until t equals to 5. Next, when you want to draw a positive cash flow, that means money is flowing into the system, money that is being earned by the system, you draw it with an arrow pointing upwards. Right? So this arrow here indicates that money is flowing into the system at t equals to 0. So I have here another example, a positive cash flow at t equals to 5. So money is being earned at year 5. So both of these arrows indicate positive cash flow, that is incomes. So conversely, if I want to draw a negative cash flow, that means money that is flowing out of the system, you draw them by using arrows pointing downwards. So arrows that are pointing downwards indicate negative cash flow, that means cost or expenses. And one final thing to remember is that the length of arrow indicates the amount of money for that particular cash flow. So for example here, as you can see, the cash flow, the arrow for cash flow at t equals to 0 is slightly longer than the arrow for the cash flow at year t equals to 5. So this indicates that the amount of money at cash flow t equals to 0 is bigger than the amount of money at cash flow t equals to 5. Now let's try this simple exercise to draw a cash flow diagram. We are going to draw a cash flow diagram based on this information. So we have a uniform series of $4,000 per year for 5 years starting year 3, and we have a deposit in year 2. So our total number of periods in our cash flow diagram should be 7 years. So let's draw our cash flow diagram. So we are going to draw this cash flow diagram based from our perspective. For the deposit, it is as though it is us that is paying the money for the deposit, and starting from year 3 until year 7, it is as though it is us that is receiving the annual payments of $4,000 per year. So in year 2, we pay a deposit. So because it is a deposit, it is money that is leaving us. It is a negative cash flow. So we draw the cash flow of the deposit with an arrow pointing downwards. So that's our deposit in year 2. Don't forget your label. And then we have a uniform series of payments that we receive every year for 5 years starting year 3 of $4,000 per year. So because it is money that we receive, so it is a positive cash flow. So we draw the cash flow with an arrow pointing upwards. As always, don't forget to label your cash flows. And finally, it is a good practice to state the interest rate on your cash flow diagrams. So that's it. This is our first cash flow diagram for this course. Now here's another example of a cash flow diagram which is slightly more complicated than our previous example. We have cash flows over an 8-year period starting at year t minus 7 until t equals to 1. For every year there is an income and cost. From there you can calculate the net cash flow of that particular year. So for example, at year t minus 7, the income is 0 and the cost is $2,500. So the net cash flow for that particular year at T-7 is minus $2,500. So this is drawn here. An arrow is pointing downwards at T-7 and the amount is indicated there. Similarly, at year +1, you have a total income of $900 and a cost of $275. So that gives you a positive net cash flow of $625. That is drawn here at T equals to +1. The arrow is pointing upwards, indicating a positive net cash flow, and the amount of $625 is indicated. So here's the final topic in this lesson, which is about MARR, minimum attractive rate of return. Now, MARR, as the name implies, is the minimum rate of return that is required when evaluating alternatives. So, in other words, MARR is the lowest rate of return that companies or individuals are willing to accept when investing. When an alternative such as a project or an investment proposal offers a rate of return that is higher than MARR, then that alternative is economically justified. But if the alternative offers a rate of return that is lower, that is less than MARR, then that alternative is rejected. So MARR is usually established by the financial managers of the firm, and MARR is fundamentally tied to the cost of capital. So for example, if the firm decides to embark on a project, then the loans that are undertaken to finance the project will be charged with an interest. So those interests is the cost of capital for financing that project. So therefore, MARR must be set higher than the cost of capital that is incurred by the firm, and the MARR must also be higher than the rate of returns that are offered by other safe investments. Now here's a simple exercise to test your understanding of MARR. There is a proposal for an investment of 1 million ringgit in a project that offers a rate of return of 5% per annum. But you don't have 1 million ringgit of spare cash lying around, and a bank loan of 1 million ringgit will be charged with an interest rate of 6% per annum. So the question is, what is your MARR and why? So your MARR should be 6% per annum, and the reason is because that is your cost of capital. That is the interest rate that is charged on your bank loan of 1 million ringgit. So the project must be able to offer a rate of return that is at least 6%, just so that you are able to service your loan, just so that you are able to pay the interest that is charged on your loan. The second question then is, should you invest in that project? Now the project offers a rate of return of 5% per annum, which is less than the cost of your capital, which is 6% per annum. The rate of return that is offered by the project is less than your MARR. So therefore, you should not invest in the project. The project is not economically justifiable. On another note, you could consider to invest in the project if the interest rate that is charged on your loan could be reduced to 5% or less, or if the rate of return that is offered by the project could be increased to at least 6% per annum. Right, so we have concluded chapter 1. Here are simple problems for you to try, and we will discuss the solutions in class. Thank you for your attention.